so first we start with, of course, adab, okay, which is B5, the element of create hubungan dengan Tuhan. All right. So technically, well, scientists investigate that which already is, and engineers create that that which has never been. Okay, so this is a good quote for us to reflect. Okay, for us as being an engineer, inshallah, for you guys. All right, so learning outcome. Okay, so the learning outcome from this topic will be first able to calculate the transmission length of the pre-stressing wires, which is we'll cover for CO2, PO3. Second, able to calculate bond stresses developed between concrete and steel, and we have third, able to determine the stress distribution, able to determine the bursting tensile stresses in the in en bloc. Okay. All right, so now the first concept we're talking about en bloc. So what is en bloc? So when talking about en bloc, we are talking about a beam. Okay. Okay, so when we design our stress block, when we design our pre-stress beam, so technically we already designed the tendon as well. So it means that this is the beam, and we provide the tendon probably somewhere here. Okay, so I'm not sure why there's a sharp thing appear whenever we try to make a straight line. Okay, avoid lah. Okay, so the thing about this thing is whereby when you want to provide en bloc is where the position of the forces applied, which normally it will apply somewhere here. So this is where you have your forces, okay, your P, and then this is will be your P. So technically you have your P, and you will have your P. Okay, so so when you apply a force here, a big force, you pull the tendon out. So technically, there will be a concentration of stresses happen here, somewhere here. So therefore, when there is a concentration of forces appear here, so the tendency of bursting or rupture, okay, of the concrete will be critical at this point. So this point. So here is whereby it has to be heavily reinforced. So it means that you have to provide shearing at that particular position. So the question is, when we design out, this part, all right? So this particular part is where we call it as a, we call it as a, this part, this particular part is where we call it as a stress block. Okay, not sorry, stress block, en bloc. Okay, so we call it as en bloc because normally the position of it will be at the end of your beam. All right, so when talking about en bloc, it happens because of the concentration of the forces. Concentration of forces here that applied, which is you have stress P when you pull. So technically, this is what we call as a Hoyer effect. The radial pressure will be like circulate inside and will cause a friction, which will triggered the tendency of it to burst, to rupture, to spoil, and things like that. All right. So what we can do to avoid this from happening is by providing a sufficient amount of shear link, at the end of your beam. Okay. So the question will be, how long is the link that we need to provide? So the question will be this particular question. Okay. The question. So it will be like this particular length. Okay, so how much? Okay, how much? The length that you want to provide the what we call the shear link. All right, so that will call as a transmission length. All right, so technically we can say that the forces that apply, the radial pressure that can cause the bursting, and you will provide shear link to avoid it from happening. So what are the concept of how the bursting can happen? By applying the what we call as a Hoyer effect. So the transmission length, so where we have to provide the reinforcement or the shear link, generally we take about 50 to 100 let me, okay, 50 to 150 times the tendon diameter. All right, so this is kind of like the assumption that we can make. Okay, we either can take 50 to 150 times the tendon diameter. Say that if we provide like the diameter of our tendon, probably like 16 mm, for example. So then you can provide the length would be multiplied with 50, or we could also multiply with 100. Then it become like 100, 1,000, 1.2 some 1.16 1.6 something, okay, meter. So technically, this is where we classify it as a transmission length. Okay, so if we cannot assume, or we don't want to assume, we want to we want to propose the actual length, of where we want to position our shear link, we can go through this formulation. Okay, so this formulation is whereby you have alpha 1 multiply with alpha 2 multiply with phi, right, multiply with stress PM naught divide by your bond stress, which is BPT. So alpha 1, it really depends on the method you release the tendon. So if it's a gradually release, you can take it as a 1.0. If it's taken like a sudden release, you can take it 1.25. Okay, so second parameter will be alpha 2. So alpha 2, it will be depending on the type of wire or type of tendon. So the type of tendon could be wire, it could be strand, it could be tendon, it could be others. So in this option, we are given two options. So it depends on if you are using wire, so you can take 0.25. If you are using like a wire strand, right, 3 to 7, then you can take it 0.19. Or if you are not sure, if you it's not wire or tendon or a strand or whatsoever, so you can refer in terms of the comparison of how big it is to the compare of round wire 0.25, or you could like equivalently taken as 3 or 7 wire strand, so then can be taken as 0.19. Okay, so then we have another consideration, which is your diameter, nominal diameter of your tendon. And then you have your tendon stress. So tendon stress is calculated, yeah, by PI, which is the initial tendon force, divided by your area of your tendon. So then you will get your tendon stress during transfer. So when it's during transfer, you have to aware that your PI will be initial pre-stress force, okay? And you have the bond stress. So bond stress can be calculated by taking your mu P1 multiply with mu1 multiply with your tensile concrete design, okay? And you have your mu P1 here can be taken as depending on the type of tendon. If you're intended wire, then 2.7. If it's a strand, then 3.2. So if you have mu1, it is considered as a bond condition. So if it's a good bond, you can take it as a 1. If it's a other condition, you can take it as 0.7. So how to calculate FCTD? So technically, you can take the FCTM from the table 13 in the Eurocode, multiply with 0.7, divide by your gamma C. So gamma C can be taken as 1.5. So technically, you can calculate your strength for your tensile, okay, of the concrete. So put all the parameters inside this equation, you can calculate your transmission length. Okay, boleh everyone? Are we clear? Okay, so once we calculate the value of your LPT, so technically you have to, the design value, when you want to decide the design value of your LPT should be taken as the less favorable of two values depending on the design situation. So technically we have options whereby it's either 80% of your LPT or your 1.2 of your LPT. So you can take which one, the less favorable between these two. So normally the lower values, okay, is used for verification of local stresses at release, and the higher value can be taken as the ultimate limit state design for the shear and also anchorage design. Yeah? Okay, so when we want to calculate our transmission length, we can also use this method whereby we calculate our beta B, whereby this is a transmission factor. So this transmission factor can be taken, can be calculated by using table 8.1, whereby your beta is really depending on your strand or smooth intended wires, or is a rib wires, so then you can get the concrete grade and your beta B depending on the concrete grade. For example, if you are taking C30, 37, so then if it's a strand and smooth wires, then you can take it as a beta equal to 70. All right, so this is consideration when we want to use these values lah. Okay, it's either you use this table or you can use the formulation to get your transmission line values. Okay, boleh everyone? Are we clear?
Clear, Doctor.
All right. So in post-tension member, okay, the force is concentrated over a small area at the end faces of the member, and this leads to high tensile forces at right angles to the direction of the compression force. So these effects will extend some distance from the end of the member until the compression has distributed itself across the full concrete cross-section. This is what we mentioned, that the concentration will be at the end. Okay, so this region is known as en bloc, okay, and must be heavily reinforced by steel to resist the bursting tension forces. So en bloc reinforcement will generally consist of close link which surround the anchorage, and the quantities provided are usually obtained from the empirical methods. Okay. All right, so this is end zone design for pretension. So in pretension concrete beam, the prestressing force is transferred from the tendon to the concrete over a short transfer zone near the beam end. So technically, due to the concentrated tendon force at the end region, transverse tensile stresses are generated within the concrete end block. Okay, so therefore, when if this tensile exceed the tensile capacity of the concrete, so technically the crack will appear. All right, the splitting may develop lah, so it will occur. So you want to avoid this. Want to avoid this from the crack from appear. So we have to provide what we call as transverse reinforcement. So this transverse reinforcement or the shear link. So this where we can provide it by taking this formulation. Consider this formulation whereby we have ASV equivalent to 2.5 M. So M is the resultant bursting moment at the end zone. And we have the FS, which is the permissible stress in reinforced steel. And also the H will be the overall height of your beam. So this will be your area of your transverse reinforcement, okay, at the end. So when we design the M block, okay, what to be considered, right? So especially when you have your post tension. So when you have post tension, we know that post tension will provide anchorage system. So anchorage system will have different type. You could have flat plate, maknanya you have a plate here, or you could have what we call as conical anchorage. So means that you have conical will be like penetrating into your end block, or end part of your beam. So if you look into the stress distribution, if you are using flat plate, this is your stress distribution. It will be different from your conical anchorage and stress distribution. Okay, so this is giving us some input on how we want to provide, how much we want to provide our reinforcement. Okay, because it will affect in terms of determine how long is your transmission line. All right. Okay, so anchorage zone failure due to uncontrolled cracking or splitting of the concrete from the insufficient transverse reinforcement. So bearing failures immediately behind the anchorage plate are also common and may be caused by inadequate dimension of bearing plate and also poor quality of concrete. So there will be so many factors to be considered that can contribute to the failures, right? So then therefore we have to provide a sufficient reinforcement to it. So technically, if you look here, the first picture or the first figure, you can see that the reinforcement is heavily reinforced at the end. Okay, and this is the strand. Okay, multiple numbers of we consider this probably wire. All right, and you can see the wedge or the it looks like a something to lock into. And then you can see the ducting. Okay, so and also the reinforcement provided for the beam. Okay, so technically when we say crack, okay, so normally when we say crack and we are providing our shear link, so we cannot, avoid of considering the diagonal cracking that might occur due to the crack, ya. Uh, Kenapa pula ada yang request ni? Dah minggu ke berapa dah baru nak request? Okay. So when we have a transmission, forces, so transmission forces in the end block, it really depends on the anchorage system, especially when we are dealing with post-tension method. So post-tension method will have anchorage system. So anchorage system whereby the concentration of fluid will depend on the anchor plate. So if you have one anchor plate like this, so the concentration will look something like this. So then providing the link will be totally from here to here considered as your transmission line, or probably here. Right. So if you have double anchor plate, so technically you have like two up and down, depending on where you place your anchor plate. Okay. All right. So just now we designed for our shear. Okay, so this one is where we could design the end block by checking the bearing stress. We can also based on the bearing stress check, okay, to ensure that the provided area and the gap is sufficient enough, for it to retain the design part, which is will not burst, will not split, or will not crack. So technically, we have in the design it necessary to check that bearing stress behind the anchorage plate due to the pre-stressing force does not exceed the limiting stress. All right, so means that the bearing stress of the anchorage plate. Okay, so how then the value of the limiting stress that you can calculate is by taking 0.67 FCK AC1 divided by AC0 multiply with our power of 0.5. So this equation must not less or equal to 2.0 FCK. So if it's not, if it's more, so means that you have to calculate back your design, okay, so that you're gonna get it small, what we call smaller than 2 FCK. Okay. So as AC naught, what is AC naught? Is loaded area of the anchorage plate. AC1 is the maximum area, okay, having the same shape as AC naught, which can be inscribed in the total area AC. Okay, so this is where it identify the position of AC naught and also AC and also AC1. All right, so technically it classifies itself in terms of the area, okay, and you can see that the resultants of the forces when you apply it, okay, it has like resultants of to represent the crack, which is diagonal part. So the resultant, of course, the straight line between these two, and the theta open is around 30.7 degrees, yeah. So this is where we call as a dispersed angle. So technically the lateral tensile bursting forces can be established by the using of statically determinate strut and tie model, where it's assumed that the load is carried by a truss consisting of concrete strut and links acting as steel ties, which is we could have the partial factor or safety equivalent to 1.2. So you can see that dispersed angle of the compressive strength, which is stated by the code, should not exceed 0.4. Okay, 1 minus FCK divided by 250 FCK. So if the reinforcement is designed to 0.7 FYK, as we know, limited to 300, so means that no crack check is necessary because it's already reached the limit. Okay. Boleh everyone? Are we clear?
Boleh, Doktor.
All
Yes,
right.
doctor.
Okay. Okay, tak apa. Nanti we will look into the example so that you can have a better picture. So at the aviator, shall identify the following requirements. So we stand both longitudinal and transverse forces that the tendon applies to it and transmit these forces to the structure. Second, ensure that the radius of curvature of the pre-stressing tendon does not cause any overstressing or damage to it. Okay, so that will be condition. So you can see that if you have a flat plate anchorage type, anchorage is this, normally for post tension. So you will see that the stress distribution will look something like this. So if you have conical anchorage, which is the anchorage is penetrate inside, so you will have it, the stress distribution is like this. Okay, so typically, typical flow lines of compressive strength, which is figure E and also figure B. So whatever type of anchorage used, the distribution attained at distance from the loaded face. So lateral dimension of the member. So relatively independent of the anchorage type. So distributing of tensile stresses at in figure 3.C, which is this figure. So you can see that this is the flat plate anchorage. So this is the two what you call the values, all right, for each here. And then you have the distance from the surface, which is this is the possible bursting tensile strength that this beam will experience. Okay. All right, so anchorage zone, which is en bloc reinforcement. Okay, so we have the main reinforcement in the anchorage zone should be designed to withstand the bursting tension, which is determined by the transverse stress distribution on the critical axis, usually coinciding with the line of action of the largest individual forces. Okay, so for plate and embedded like phrase, net, type of anchorage, the typical arrangement of the forcemen in en bloc is shown in figure. So mat, helix, loop, and link are generally provided in perpendicular direction. So based on research work, helical reinforcement is much more efficient. Yeah, if you want to compare it with mat reinforcement. So let's have a look. So this is where we have the hairpin. This is like a mat look links arrangement. All right, that can be referred. Okay. All right, so this is the post-tension tendon and also the anchorage picture. So this is an example taken for en bloc reinforcement pre-tension. Okay, taken from a book. So as you can see, a pre-tension beam of 8 meter. Okay, span has a symmetrical I section. So let's try to like just okay. Okay, so it's 8 meter. Okay. The dimension is shown in figure. So the member is pre-stressed with 8 wires of 5 mm diameter. Okay, located on the tension side. So means that below, bottom, this part. Okay, this part. Effective eccentricity of 90 mm. So means that they already calculate the effective eccentricity, which is considering all eccentricity of the wires, okay, to your neutral axis. So they take around 90 mm as the average or effective eccentricity. So the initial stress is taken as 1,289 Newton per mm square, okay, for the tendon. And also the cube strength of concrete is 42 MPa. All right. So if you look here, you have determined the maximum vertical tensile stress developed in the transfer. So you have to calculate the vertical tensile stress, okay, developed in the transfer. Okay, and then design the suitable mild steel reinforcement. Okay, for to cater it, assuming the permissible stress as 140 MPa. Okay, now let's take a look. Yeah, don't bother about this yet because we are going to concentrate on the beam first. Okay, the information given in the question. Okay, what we have to calculate now is calculating the total stresses because you want to, in terms of for us to design. Okay, in terms of for us to design, what will be the provided, link that we want to provide in for the en bloc. Okay. Okay. So first of all, we need to calculate the pre-stressing force. So for us to calculate the pre-stressing force, we can put it the values of your initial stress, which is given in the question. The initial stress is 1,280. Okay, 1,280 is the is your stress. Okay, so stress multiplied with the area is and then you get your force. So for you to calculate your pre-stressing force, you can use the pre-stressing stress of your tendon. Then you multiply the area. So the area is multiplied with 8, whereby the 8 is the total number of wire that you have, and the diameter of each wire is 5 mm. Okay, so this will give you the value of your pre-stressing force. Initial pre-stressing force is 200 kN. Right, so for us to know what will be the total stresses, okay, remember the condition that we we can calculate, okay, for our beam, our pre-stress beam. Okay, so we will consider the values due to the pre-stress only. Okay, we take the value due to pre-stress because we want to provide the what we call the link, okay, the shear link at the M block, which is the main failure or the main cause of it will be the P, not because the crack at the end part of your beam is not caused by the load applied on the beam, right? The possibility of it to fail at the end of the beam, which is we want to design our end block, is caused by the pre-stress force. So therefore, we want to calculate only the stresses that contributed by our pre-stress force, which is we have P over A plus with PE over Z, and also PA over A minus PE over Z. So technically we'll get stress at the bottom and also at the top. So we get 8.6 mm Newton per mm square, and we get 0.006 Newton per mm square. So technically we have two values, yeah. So dekat bawah, right? Dekat bawah, the bottom part, we get what we call as a 8.6 kat sini. Okay. Macam silap ni, bukan zero. This one is zero, ni ada typo kot. Sorry, betul lah. So at the top, we get it zero. So 0.06 here, Newton per mm square, is actually equivalent to zero lah. Okay, so this is what we get, 0.006. Okay. Boleh, everyone? Are we clear till to that? Okay. So when we want to calculate the moment from the stress block, okay, our assumption or our consideration is whereby we know that we have two different area, right, for us to calculate our stress block. So the forces that will be applied will be at the center point of your section area. So you have this part which is contributed, the stress is 0.64. Okay, how we get the 0.64? Sekejap. Tadi. Tak apalah. Okay. Okay. So we will use the triangle punya consideration. All right. So whereby we take the values of 8.6, which is the whole stresses at the bottom, okay, divided with the 400. So this will be equivalent to X divided with your 170 contoh. So because you have two ratio of your X kan, right? Then you will get the value of 0. Nanti boleh calculate lah. You will get the value of 0.64. Okay, you get the interpolation of it lah. All right. So this particular point, whereby with the distance of 170, you will get 0.64, and half of this part, this particular part, which is the height, is around, maybe we can have it 400 minus 120. So half of it, this one, you will get this distance will be 70 mm. All right, so half of this point will be contributed by these stresses when you do the interpolation. Okay, so you can estimate lah the 100, what we call the distance from down to up, and also the triangle interpolation for us to get the stresses at that particular position. Okay, boleh everyone?
Boleh, Doktor.
Okay,
Boleh,
alright.
Doktor.
So then
Doktor, nak tanya boleh?
yeah, please.
Apa tu nama dia? Yang tadi nak
Tak dengar.
8.0 over 400 tu kan? Saya dapat 7.955.
7.9. Oh, saya sebenarnya dia tak lengkap ni. Kejap. Kalau you nak I calculate, there will be, kejap. Dia bukan exactly 170 ni. You kena ambil this particular part, the distance is not 170. The distance here to here is 170. So this one dia punya Y dia berapa tadi? 60 minus 30. So kat sini 30. So the distance is 30. Silap. Cuba you dapat 8.6 minus divided by 400. Dapat 30.
Dapat doktor 0.45.
So you dapat 0.64 kan? Okay. So tak habis cerita. Alright, so the same. Dia ambil, because why you ambil this particular triangle. Kalau saya padam. Okay, so you will take this particular triangle, okay, which is we are considering the height of this part. Okay, and another triangle that you will consider would be this triangle. So another triangle will be this triangle lah. So triangle yang ini pula. Maknanya daripada atas sampai bawah. So you akan ambil the height daripada sini ke bawah. Untuk get the 2.8 ni pula punya stresses. Okay, boleh?
Boleh doktor. Terima kasih doktor.
Okay. All right. Then we have your moment. Once you know the stresses, okay, you know the stresses for each, okay, then you can calculate the force. Okay, because technically this is the value of your stress. Okay, this is the value of your stress, which is you have 0.64 and also 2.8. Okay, and these values is your area. So this is the area of your flange and this is your area of your web. Okay, so technically your area multiply your stress, you will get the force. The force multiplied with your lever arm. Lever arm will be taken like 170 from your neutral axis and 70 to your neutral axis. Okay, so then you will get 170 and also 70. So the total moment that required for the beam, okay, that caused by the tendon forces or the tendon stresses will be equivalent to 351 times 10 power of 4 Newton mm. Okay, so that would be your moment, what we call the internal moment due to the stress distribution. So once you get that moment value, so you need to know how much is the length you want to provide your stresses. So for us to calculate your length, you can use this formulation. All right, and then you take all the parameters into it, then calculating it by putting it into equation, you will get 397 mm. Okay, so that will be your total stresses, transmission length. Yeah, so it's a transmission length. Okay, so once you get your transmission length values, so you can calculate or you can use this, you can take 397 mm as your transmission length, or you could use this formulation. Okay, either or, some other you use that formulation or you can use the table. So for you to use the table, okay, you need to find your beta B. So beta B can be found by taking the concrete grade and then the type of wire, which is here you take 65, multiply with the diameter, which is 5. So you get it around 300 to 5 mm. So you look into the difference, it's not much difference lah. So it's still like 300 plus transmission length. So plus minus. And okay, boleh everyone so far? So, all right. Okay, so when you take the steel stresses is 140 MPa, limited to 300, which is where we provide no check on crack. So the required what we call reinforcement that we can use or we can provide for our shielding for what we call for our end block, whereby we can take this formulation, okay, where we take 2.5 multiply with the moment and capacity that we already calculated just now based on the stress contributed from the tendon, and divide by your strength multiply with your height, you know, your height of your beam section. So total around 157 mm square. So for this, you know that, okay, you need to provide what we call link with the area of 157. So we can provide like 3 with a 6 mm close link. Say it's around 50 mm, 200 and also 250 mm center to center. Okay, boleh for the first example. Okay, all right. So now we go to the second example. All right. So second example where we're gonna cover for the another method whereby this is where we provide what we call as a conical. It's a for post tension. Okay, this is example for post tension. Yang this one is example for pre-tension. Okay, and this example is for post tension. Okay, so for post tension, okay, for example, if you look into here, so the beam below is stressed by 4 analytical 100 mm diameter conical anchorage. Okay, so located as shown and with jacking force of 250 kilonewton applied to each. So the area may be subdivided into 4 equal end zones. So when you have a conical, remember the conical type of anchorage. So kalau kita kata conical tu means that dia akan it will be penetrated. Dia bentuk dia macam ni, conical. Dia masuk dalam. Alright. So dia bukan plate. So bila dia conical tu dia akan something like this lah. So dia punya stress distribution tu will be like this. Okay. Alright. So when we have the conical designed the what we call the anchorage. So technically that's why we will look into the figure here dalam picture ni. You can see this is circular because it's a conical. Dia ada diameter lah, dia bulat-bulat kan. Alright, so it's a circular shape. Alright, because it's the conical. If say that it's a flat plate, okay, plate biasa, then you have it rectangular lah. Okay, but if it's a conical, then you can see it has like a diameter. So for each tu, dia akan apply, dia akan tarik 250 kN for each. Alright, so when the area may be divided into 4 equal zone, which is kita ada 200 times 150. Maknanya we consider the each area tu, for each tu, dia ada 200 times 150 each. Okay. So determine the reinforcement required around the anchorage. Berapa kita nak provide? Setiap anchorage tu will have a loop punya shear link. Alright. So for us to strengthen the end part of the beam when we have the near to the anchorage system. Okay, so FCK is 40 MPa, FYK is 500. So say that you want to design for one anchor je. Maknanya it's not for 4 anchor because the design will be the same. But you want to know how much is the link, shear link that we want to provide at that particular area. Okay. All right. So now let's say we have the check bearing stress under the anchor. So actual bearing stress, how you want to calculate the bearing stress is by taking the gamma P, which is 1.2. So we know that kalau if we have gamma C, gamma for partial factor or safety for concrete is 1.5. Gamma partial factors safety is for steel is 1.15. Well, you also have gamma P, which is for tendon force, pre-stressing force, which is we equivalent to 1.2. Okay, or sometimes taken as 0.9. So kena tengok lah. Alright, so gamma P is taken as 1.2. So multiply with pre-stressing force, meaning for each force tadi, dimension, dia tarik 250 kN. Alright, so we know that the load is 250 kN. So when you divide by the area, you know that the stress tu is 38.2 for one anchor. Okay, for one area lah, because the diameter of your anchor tu is given as 100 mm diameter for the anchor, for the conical anchorage. Yeah. Okay. So when you have the actual bearing stress, meaning how much stress that applied, when tarik itu what will be the stress. Okay, so the allowable, then we can use this formulation to calculate the allowable. So how to calculate the allowable is by taking the resistant force is 0.67 multiply with FCK, and we multiply with area of C1. Okay, divide by area of C0 and square it with 0.5. Okay, so power of 0.5, sorry. So AC1, if you look into the AC1 part, is considered as this area, the minimum, the area of the concrete yang luar from the conical part, which is 150. So, but then you can see that this one is rectangular, but since that we are considering it circular, so then that's why we take it as a diameter, maknanya 150 mm. Okay, and we say the 100 is the conical diameter lah, which is 100. Okay, and divide by 4, you get the diameter for area for each, and you get the total resistance is 40.2 Newton per mm square. So the resistance is obviously more than the applied, which is 38.2. Okay, the actual bearing stress. Okay, so technically, then we want to provide our what we call from figure B. We want to provide figure B. Okay, this one. Okay, we want to provide the tensile force in the tie with the equivalent thrust is given. So technically, we can use this relationship whereby the T or the tension force, okay, equivalent to 0.3. We can take this relationship because we are providing the link to is vertical, tegak-tegak kan. So the relationship between, by considering the crack that will happen, the theta is around 33.7. Okay, and the resultant of it to provide the resistant force will be 0.33 P. So then we will take P as a 1.2, okay, multiply with 250, which is the force. So technically we have 100 kN, okay, for the tensile stress. So how much we say, if the area of the tensile stress still is required, so the strength that we will need to provide is limited to 300, yeah, is limited to 300. So then we can provide the area of reinforcement that we can provide is 330 mm square, because this is your strength limit of your link punya strength lah. Okay, so then you can provide the area is 330 mm square. So this can be provided by 3. You can provide lah 10 mm link. Okay, which is a total around 471 mm square contoh, and you have the center to centers 50, 125 and 200 mm from the end face that is distributed through the length lah, to the length. Okay, boleh? So far are we following?
Yes, doctor.
Okay, so you can see that this is provided 3 T10 here. Okay, maknanya dia akan susun lah 3 T, ada 3 line, 3 numbers of T10 kat situ. Alright, and number C, the question dia tak ada mention question totally kan. Okay, saya pun lupa nak crop the question. So the question is, the C question, they ask us to check the compressive stress in the strut. So when you want to check the compressive stress, because just now we check the tensile stress, how much it requires kan. So now we check for the compressive. So when we want to check for the compressive, you can use this formulation. Okay, 0.4 multiply with 1 minus FCK divided by 250 multiply with FCK. So technically it's quite straightforward because you know FCK is 40, right? So put into the equation, you get the allowable compressive stress will be 13.44. Okay, so this is the resistance lah. You know, what will be the beam compressive stress, you know, can resist. So technically, the actual stress in the strut, okay, by applied, so means that it really depends on the force in the strut. So force in the strut will be relying on this. This is the force, okay, in the strut. So we have 0.6 P. So this is 0.6 P. Okay, 0.6 P. So this is all P values. So by considering 1.2 as the gamma P. So and divide by your cross-sectional area. So cross-sectional area 250. Okay, multiply with 150, which is the size, and cos what we call 33.7, which is this part. Okay, that will be the cross-sectional area lah of the distribution of the force for the compression part. So then you will get the total actual applied is actually 7.21. Okay. All right. So, and the effect of the combined anchorage can be considered by considering the total precise force of 1,000 kilonewton acting on effective en bloc 400 times 400. So it means that we have the total, what we call, this particular area is actually represented by 400 times 400, because we have 200, this is 200, this is another 200. And this particular apa area of your block lah, of your cross section kan. So when we want, we can provide it as a total 1,000 kN. Why 1,000 kN? Because, well, we have like a total from the compression, and we have the total from the tension, which is 400 here. Okay. So what we call the total precise force, considering total precise force is 1,000, we have mana tadi the value of 250 multiplied with 4. 250 multiplied with 4, you get 1,000 kan. All right. So you have 250 for each of the conical anchorage. So you have 4, so then multiply with 4, you get 1,000 applied for the whole area. So that will be 1,000. And 0.33 of multiply with 1.2 multiply with 1,000. So in terms of tensile for the capacity, you get it as equivalent to 400 kN. So from here, you get the area of steel, tensile steel required is around 1,333 mm square lah. So this you can provide it by providing 6 12 mm, okay, close link, okay, with 1,358 mm square distributed along the length. Okay, means that if you want to be detailed, that it will be according to the transmission length lah. Cuma for post tension ni dia tak provide, dia tak calculate the transmission length. But we could also calculate the transmission length. But since that the question doesn't ask the transmission length calculation, so that's why it's kind of like not complete a bit for this particular example. Okay, boleh everyone? Are we clear?